Let us have a look at a little bit more on how to complete this first assignment, some few more hints. So this is from my previous hint where we read the log file names and we start a loop here running only once, right? And then we read in the content of log file number I. So in this case, since I is only one, it's the first log file. So let's actually run this code. First, the name of the log files, and then the loop, so that we actually have the content of this. And let's have a look at the first 10 lines of this log file. Looks something like this. So you can see this is a text file without any sort of system in it. So the point is now to, from this, it's 1,507 lines of text, right? From this, we now want to collect some pieces of information. And the first is the sample ID. Collect the sample ID. If we go to the assignment text, it says to find this sample ID, we look for this particular text here in the whole file, because on the same line as this text occurs, there should also be another piece of text like this. And actually, the sample ID we are looking for is the last item here, the last word in this text. So we need to find out which line contains this text, then look at that line and see if we can collect this number from it. So how do we do this? And it's said in the assignment, it was, I said, recommended, you could say, that we should use this Styrivich function. And this is a really nice one. It's part of the tidyverse. So if we look at the help text for it, it will find matching indices. So it means you search with some text, input vector or text, character vector, right? And then pattern is what you are searching for. So this is what you search in, and this is what you search for. And in our case, of course, what we search in is the whole vector of lines that we read in here. And what we are searching for is exactly this text here. The file stem is. And how do we know that we should search for this one? Well, the only way you can actually know this when you're working in bioinformatics, this is typical. You have a big messy file like this. You know you're looking for some piece of information here. You have to look through some of these files. And that's what I have done here. I looked through some log files and I notice we can actually see it here. This is exactly the line I'm looking for. And we can see it's all, in this case, it's line number 5. So whenever I see the line that has this text, I know that, and this, I must have looked through some log files to make sure of this, right? And then I see a pattern sort of emerges. So if I can find this text here, I know that this text here also is in the same line, and this is the number I'm looking for. This is quite typical bioinformatics, searching for patterns, right, in text and collect a piece of information. So this Styrivich function will give us an index, a number. Look at here, an integer vector, right? So this gives us the line number. The line number we should look into in X, right? We have 1,507 lines. This one tells us which line to look into. So if I run this code only, we will see that line number is now 5. Yes. So actually, this is the line we want to do more with. Yes, here it is. And then how do we actually collect this piece of information from this line? Well, I wrote some hints here. You can notice that this line consists of 4 words. This is the first, this is the second, this is the third, and this is the fourth word. So if you sort of collect word number 4, you're down to this text, and this text again can also be seen as a sentence consisting of 4 words, but then with underscore as separator. So then it's 1 word here, 2, word 3 here, and word 4. I will now do it in a slightly different way here actually, because I notice right away that if I split this whole sentence only by underscores, then the first word will be this one. No, this one. That's the first word. Second word will be this one. Because blanks now mean nothing. If I only use underscore as separator, then this is third word, fourth, and fifth here. So word number 5. Or if you look at the help text for word, and this is quite nice to be aware of, word can actually enumerate from the end. If you use a negative index, it means it counts from the end, just like in Python. This is not usually in R, but this particular function has this behavior. So if I word, and then which text should I look for words in? I should look in this text here, right? This is the text I want to look into. And which word do I want to collect? I want to collect the last word. So I use -1. Like this. And then I have to tell Word to use as separator this underscore. Otherwise, by default, it will use the blanks. And if I don't do this, I will collect this hold here. But now, since I specified this underscore as separator, I will only collect this one. Let's run this and store it into something. Sample ID text, I call it. And you will see shortly why I call it that. If I run this line now and have a look at this sample ID, ID txt, there it is. The last piece of text here, the last word you could say. When you split the words by each underscore. And the only thing I need to do now is to convert it to a number. Sample ID equals as numeric of sample ID txt. And as numeric will convert a text that contains a number into a proper number. So if I run this text here as well, this line of code, you will now see that sample ID is indeed a number, because here it was, this is a text, we can see by the quotes around it, this is a number. And the only reason we want it as a number is because when we read in the file sizes up here, I can actually do that. And look at that size table. You can see we have the sample IDs here. And if you actually look at this size table, I called it. Size table, sample ID. You can see these are numbers, right? There are no quotes here. And here's actually the same sample ID. So these are numbers, and that's why I also want the sample IDs here to be numbers, so I can compare them. Otherwise, you cannot join this table with the results I get here now, unless this sample IDs has the same data type. Okay, so that was the sample ID, and now you need to collect the memory usage and the time in the same way. And I will not, it's the same type of idea, right? You look up line number of a certain text, then you collect the corresponding line, and notice that when you collect the memory usage, you search not for the line with the information you seek, but 3 lines before, and that has to do with there is no sort of pattern text in the same line where you have the memory number, but it's always 3 lines above. Yeah, it's the same type of idea, and the same with time. But when it comes to the time, you have to collect also the unit. So not only the actual value, time that was used, but also the unit, because sometimes this is in some log files, it's displayed as days, and some log files, it's displayed as minutes. I'm not sure if there are other units as well. I don't think so. And then you have to make so you actually have to collect a time, right, as numeric of something here, and then a unit, which is not a number, it's a text, right? And then you have to convert the time to hours. So let me comment out these two, because these are not fully working code lines. And then you have to test here now. If unit equals days, then you have to convert time to hours. If it's how many hours are there in a day? So if time is 1 and unit is days, then time should be times 24, right? So if the value of time is 1 and the unit is days, 1 day is the same as 24 hours. So then time should be, the old value of time should be replaced by the new value, which is the old one times 24. Else, if unit equals minutes or something like that, then you have to say that time is equal to, how many, if you have 60 minutes, it's the same as 1 hour, right? So you have to divide by 60 here. Something like that. Then finally, you have to collect or put the collected data into some table or data structure, because otherwise it will be overwritten, right? So if you run this from 1 up to the length of this log files, like this, each time you read a new log file, this will get a new value, and this here, the other ones below here, will get new values. So you will lose the old ones unless you have stored them somewhere. And then I would actually make myself a table here and call it whatever you like, memory time table. And you can create tables in several ways in R. I love to use this table function. And then I put in some columns now because I already know which columns I want to have. I want to have a column containing the sample IDs. So it's natural to call it sample ID. And this should eventually be filled in with numbers, right? And then I fill it in with numbers now. And any number will do, because we will replace this number with the proper numbers inside here later. So I just fill it in with some zeros. I think that's nice number. And how many zeros do I want? I know that this table should be having one row for each log file. So actually the length of log file names, the same as the number of iterations we do in the loop here. Quite typical, right? That you use a for loop in order to walk through a data structure of some kind. So this is now the first column, and then I need a second column with memory usage, and that will also be a number, I think, so I can just copy this and use it again. And then, sorry, like this. And then time. And then I'm done. So if I make this table here now and look at it, it should now be a table with the 3 columns I need and with 32 rows that I need and filled with zeros. And now I need to sort of fill in here. And that's the last thing I do here now. So I say that, okay, this memory time table, the column called sample ID, element number I should now get the same value as the sample ID value I have, the sample ID object I have here. So please make sure you really understand the difference. This is an object, local. This is a name of a column. It's the same text that we use as a column name in this table and out here as a separate object. Well, that's legal. You can see we have the sample ID object here. And if you click open there is also a sample ID column here. These are 2 different things. They just happen to have the same name. If you feel uncomfortable, change the name of this one. I would say the column name here is more important to keep. And then of course the same for the memory, and should be equal to something here. I don't know. That will be in this chunk of code where you collect the memory, and then of course the time column, something here, time or whatever, yeah, would be computed up here. So the important point is of course this here, to index with, so that in the first round of the loop we fill in the first row here, row number I. And then when I is 2, second row loop, we fill in row number 2 here, and so on. So when this has completed now, all the rows should have been filled in with some proper values instead of these zeros. In order to plot this, I would use ggplot. And the input to a ggplot, let's store it under some name, figure. The input to ggplot is typically a table, and then it will be this table then. Oh, sorry, I should first join, shouldn't I? I should join this with the size table up here. Yeah, so we have all the columns, not only these 3, but we got a 4th column with file size here. Okay, so let me call it final table or something like that. I think it said use full join to join the 2 tables. And then you join the first table with the second table, and you have to specify which column do you want to use for binding them together. And then it's this sample ID column, because this information both tables have. The size table has a sample ID column here, and this other table also has a sample ID column, and it should get some proper values, right? The same values as here, but they may not be in the same order. And that's why we use this join function, because this will take care of the sort of joining. So the rows in these two tables doesn't have to come in the same order. They will now be joined in the proper way anyway, as long as they both have this column that we can use for reordering the rows, you could say. And then you will typically use this as input here and plot. I think I would plot it as points, don't you think? And then the aesthetic should indicate which variable do you want to have on the x-axis. And if I'm not mistaken, it should typically be the file size. Wouldn't that be most natural to have on the x-axis? And then on the y-axis, one of these other two, either the memory or time. And then you can add some more labels or stuff here, so that you can have some proper text on the x-axis. File sizes in gigabytes. Yeah, you should remember to do that conversion as well. And the text on the y-axis, yeah, memory usage in the case where memory is the y-axis variable. And if it's time, you have to change the text here, of course. Otherwise, it makes no sense. And then you print the figure. Actually, to make two figures together, yeah, I'm not going to talk more about that here now, I think, because that's something you can puzzle with on your own. I should just briefly mention it was also, you were also supposed to run a small regression analysis here to fit a regression model using this LM function. So in order to do that, you can read about it here, but this should actually be familiar with from basic statistics, right? So then you have to decide what should be the response variable, and then some, yeah, so for instance, this memory, I suppose, could be used as a response, and this file size as the regressor. It's typically the same as you plot here, right? And the data is then in this final table. Yeah. You can find a lot of information about this, I suppose, on the internet if you have to repeat it. And then you have a fitted model, and then you can use the predict function here on this fitted model. With some new data. What is it called? New data, like this? Predict LM. Whoops. Here is the help text for that one. Yeah, new data in one word. You have to create a new data frame then with the new file size. I don't type anything here now, but that should give you the prediction. And then you can ponder a little bit about this last question here about how much memory would you reserve for doing the assembly? Because what you get from a prediction is, of course, the expected value. But when it comes to the actual memory you reserve, it should be a little bit more, right? Because the expected value, it means that sort of half of the times you will use a little bit more, and half of the times a little bit less than the average, right? The expected value. So it's important to use enough memory, otherwise everything crashes. So we should actually use more than the expected memory. But how much more? Well, you can always try to write something here. I can only say that if you want to compute a confidence interval for the regression coefficients, this function here is very nice. And this may give you some valuable information to discuss this and perhaps suggest some actual upper limit, you could say, of how much memory we should reserve in this case. Okay, so I think that this is what I'm going to show you now, and the rest of this should be possible to fill in if you have some coding experience that you should actually have in order for, because we will need it for the later both assignments and things we are going to do in this course. So knit this and hand it in. And should you not be able to complete everything, hand in anyway. Because if you don't hand in anything, we assume you have quit the course. It's better to hand in some halfway and then you will get it back and do it finished than not handing in anything. Okay.